In our last post, we showed an application that classifies Lego bricks. First, we're going to explain how we train this vision system with a low budget. Nowadays, it is possible to train huge neuronal networks to classify a large number of objects. For our application, we generated 45 million synthetic images from 4,200 types of Legos. But when we realized that the R&D department wants to invest $200 in cloud processing for our project, we had to adjust expectations. Finally, after expending $195 of the budget in cappuccinos, we found a solution. We created a framework to train a few binary classifiers that can be trained in Azure Custom Vision free instances. First, we trained a base 2 logarithm of the number of classes plus one neuronal network to cover all types of objects. For example, 4 binary classifiers are necessary to classify 15 different objects. After the training, we take a photo of a Lego brick and run all neuronal networks to make a prediction. If we combine all outputs in a binary code, we obtain the object class ID. But if one prediction classified the object in the wrong class, we could obtain a totally different object. What if we use a Hamming code to make our prediction more trustworthy? Hamming distance is a metric for comparing two binary data strings. It is defined as the number of bit positions in which the two bits are different. In a set of strings, the minimum Hamming distance is the smallest Hamming distance between all possible pairs of strings in that set. If the minimum Hamming distance between any pair of code words is d, then the code can correct at least d-1 over 2 single errors. Using some redundant error correcting classifiers, we can tolerate some errors introduced by finite training sample, poor choice of input features, and flaws in the training model. The key of the error correcting output code is the use of extra parity bits to allow the identification of a single error. There are many ways to design Hamming codes. Here we only introduce the simplest one. First, mark all bit positions that are powers of 2 as parity bits. Position 1. Check 1 bit, skip 1 bit. Set the parity bit to 1 if the total number of ones in the position it checks is odd. Position 2. Check 2 bits, skip 2 bits. Position 4. Check 4 bits, skip 4 bits. We use the application again, take a photo of a Lego brick and execute the neuronal networks to make a prediction. Then the application searches the closest Hamming code. With this method, the application returns the correct object ID even if one of the networks misclassifies the object.